This section, VOMC, sets the stage for understanding the parameters used in the Gaussian random projection technique within scikit-learn, a popular machine learning library in Python. We'll be examining how these parameters influence the outcome of dimensionality reduction. The problem describes a scenario where we're using Gaussian random projection to shrink data from 1000 features down to 500. The goal is to maintain the distances between data points as accurately as possible. This is a common problem in data science where reducing the number of features is desirable for computational efficiency or to reduce noise without losing too much meaningful information. This sets the context of the quiz. We are given a specific task: dimensionality reduction with the Gaussian random projection algorithm. The emphasis is on maintaining the distances between data points. The key is to understand how parameters impact this objective. Let's unpack the options now. VOMC. This statement refers to the _random_state parameter. In many machine learning algorithms, randomness is involved. _random_state acts like a seed for a random number generator. Setting it to a specific value, like 42 here, means that each time we run the algorithm, we'll get the same results due to the consistent random number sequence, ensuring reproducibility. So this is likely true. Let's explore further. Here, we are looking at n_components which determines the target dimensionality after reduction. Intuitively, increasing this number means keeping more information. However, this doesn't guarantee improved distance preservation. The effect could be complex and depend on the data itself. So, we need to consider this carefully. The _eps parameter controls the error tolerance for distance preservation. A smaller _eps means we want to maintain distances very accurately. It influences the number of components needed, but it doesn't directly set it. A smaller _eps implies needing more components for accuracy, but not directly setting the number. A larger dataset often gives a better representation of the underlying data structure. More data points generally lead to a more accurate dimensionality reduction, as we have more information to base our reduction upon. Thus, this statement is plausible. This section guides the approach to solving the quiz problem. It suggests a step-by-step analysis of each parameter. The first step involves analyzing the impact of the _random_state parameter. As discussed earlier, this parameter controls the reproducibility of the algorithm. Let's proceed systematically. This section focuses on understanding how different parameters within the scikit-learn's Gaussian random projection affect the dimensionality reduction process. We'll examine how each parameter influences the outcome, paying particular attention to their impact on maintaining the distances between data points. It sets the stage for evaluating the correctness of the multiple-choice statements in the quiz. This is the core question. It presents 4 statements about the Gaussian random projection parameters. _random_state n_components eps and dataset size, and asks you to determine their truthfulness. The goal is to test your understanding of how these parameters work together. Statement A examines the _random_state parameter. In machine learning, reproducibility is crucial. The _random_state allows you to set a seed for the random number generator, ensuring you get the same results each time you run the code with the same settings. Setting it to a fixed value like 42 makes the projection repeatable. This is essential for debugging and comparing results. Statement B explores the impact of increasing the n_components parameter, which represents the target dimensionality. Intuitively, increasing the number of components should result in better preservation of information, including pairwise distances. However, it's not a guarantee. The improvement depends on the data's structure and other parameters. This highlights the complexity of dimensionality reduction. Statement C discusses the _eps parameter, which controls the level of accuracy in preserving pairwise distances. A smaller _eps value means you require higher accuracy. This doesn't directly set the number of components, but it influences how many are needed to achieve the desired accuracy. A smaller epsilon typically implies a larger number of components. Statement D examines the relationship between the dataset size and the quality of dimensionality reduction. A larger dataset provides more data points which, in turn, gives a more robust and accurate representation of data's inherent structure, thus leading to better dimensionality reduction. The more data you have, the better the projection. This section title indicates, we'll be analyzing parameters within scikit-learn's Gaussian random projection function, focusing on how these parameters affect the dimensionality reduction process. Specifically, we will investigate the impact of _random_state _n_components and _eps on the projection's accuracy and reproducibility. We'll also explore how the dataset size influences the overall quality of the dimensionality reduction. Think of it like adjusting knobs on a machine to optimize its output. This question poses 4 statements about the parameters of Gaussian random projection. Each statement will be evaluated for its accuracy in reflecting how the parameters affect the dimensionality reduction technique. It's a great way to test our understanding of the function's behavior. Statement A focuses on _random_state a parameter that controls the randomness of the process. Setting it to a specific value like 42 ensures that the random number generator starts at the same point every time, guaranteeing consistent, reproducible results. Think of it as setting the seed for our random number generator. Setting this ensures that our experiments will always produce identical results, making it easier to compare results and debug any problems we might encounter. Statement B looks at the impact of _n_components which determines the number of dimensions to retain after reduction. It suggests that increasing this number improves distance preservation. While this is often true, the relationship isn't always straightforward. Increasing components retains more information, but doesn't always result in better distance preservation because other factors might play a more important role. Therefore, this statement is not always true. Statement C discusses _eps which controls the allowed error in distance preservation. A smaller _eps means we demand higher accuracy, less error, resulting in a higher number of components to achieve that higher accuracy. Think of it as tightening the tolerance. You need more components to meet the stricter criteria. It's an indirect relationship. Statement D examines the effect of the dataset size on the reduction's accuracy. A larger dataset generally provides a more accurate representation of the data's underlying structure, leading to more reliable dimensionality reduction. More data usually means more reliable insights and better results. Think of it like having more evidence for a scientific conclusion. More data often strengthens the reliability of our result. This row simply marks the point where we would evaluate our answers to the question given above, indicating that we need to select the correct options based on our analysis. This refers to the collection of data points we are applying the dimensionality reduction technique on. The quality of the reduction process heavily depends on this input data. This is the specific scikit-learn function being used for dimensionality reduction. It's a technique that leverages random projections to reduce the number of features in a dataset while attempting to preserve essential information and distance relationships between data points. This refers to the lower dimensional representation of the dataset obtained after applying the Gaussian random projection function. The aim is to achieve a more manageable dataset size while preserving significant aspects of the original data's structure.